Yes?
So you said in that one equation that there's no approximations, yet we're still taking an average value of W. Can you explain how that's not an approximation?
So we, in finite volume, so the question is we are taking an average value of W. Why is that not an approximation, right? Because the average of W has a rigorous definition. So if you know the functional form of W, then you can actually compute the average value of W exactly, right? So we are not making any errors. We are not committing any errors by tracking the average value of W. We lose information by only tracking the average value, but we are not making any errors. All right. Yes?
How do we calculate Nij?
How do I calculate Nij? Right. So okay. So Nij is basically the integral of the normal. It's basically the area with a direction, right? So the okay, and in particular, if the surfaces are flat, which is actually most of the finite element cases, the surfaces are flat, then the Nij is basically a directional area vector, right? So the size of Nij is exactly the area, and the direction of Nij is the direction normal to the surface. And if the surface is not flat, then you have to integrate over these infinitesimal surface elements, whose definition is the same. The size is proportional to the size of the infinitesimal element, and the direction is not orthogonal to the infinitesimal surface element. All right. Oh, and also one thing to note is that Nij, by this definition, is exactly equal to minus of Nji. Okay. Right. So this ensures that basically, as long as you compute a consistent Fij, so Fij should be the same. So Fij should be the same as Fji, right? So when that is the case, this ensures discrete conservation, right? Because if you take this equation and sum it over multiple adjacent cells, the flux between the internal of these adjacent cells actually cancel out exactly, and you only get the flux from the outside of the set of cells. All right, that's kind of the discrete conservation property of finite volume. You lose it if you either don't have exactly a partition of unity, or one of these conditions didn't hold. I mean, in practice, we actually just compute a single Fij, and we add the contribution to one cell while subtract the other contribution, subtract the same contribution from the other cell, right? So once, if computationally that's what you do, you are guaranteed to have discrete conservation. Compute the flux only once for both adjacent cells. All right, any other questions? Okay, so let's just figure out the most straightforward way of approximating the flux, and let's specialize this in 1D. Okay, so let's first specialize this in 1D. So in 1D, this is nothing but the width of an interval, right? Each omega I is basically an interval, and the volume is basically the width of the interval, delta x. And this summation would be either, each cell either has one or two neighbors, right? Depending on if it's exactly on the boundary or it's not in the boundary. And so if we're considering periodic domain for now, which let's do that for now, and consider periodic domain for now, we would have basically two neighbors for every cell. And what is Nij? What is the surface normal for an interval? It's just the 1 or minus 1 depending on which side you are doing, right? So basically, if I have an interval, the surface normal would be like 1 over this side, minus 1 over this side, right? So that's and then multiplied by the value of the flux. Okay, so let's just write down this finite volume form, ddt of delta x times delta xi times wi. So let's don't assume a I just want to show you don't have to assume a uniform grid. Plus, well, let's do the plus one side first. Okay, so that's actually fi and I plus 1, right? So that's the flux between the cell I and cell I plus 1. And you can also denote it as fi plus half. Minus fi and I minus 1. You can also denote it as fi minus half, equal to 0. Okay? And fi plus half is actually should be approximately equal to the flux function evaluated at what? At halfway between the cell I and cell I plus 1. Right? Okay? So a natural way to compute the flux would be just doing the interpolation, right? So can I just how do I interpolate? So let's say I have a let me actually use the MATLAB a little bit, FE demo. So how can I interpolate the function using its cell averages? So let's imagine I have a function like that, and I want to interpolate the value here using the cell average here and cell average here. What's the best way to do that? Just the average value of these two averages, right? Take the average of the average. So the average of the average, of course, is just the simple average over the two cells. And actually, you can actually do some really nice Taylor series to say that, to figure out the order of accuracy of that particular approximation. And I can just tell you this approximation is going to be first order if the two cell sizes are not the same, but it's going to be second order if the two cell sizes are actually the same. Yes?
Suppose you know the average of all the block there, would it be better if you use, let's say, an interpolation to interpolate over the whole domain?
If I use a what interpolation? Can you say again?
Newton.
A Newton interpolation? What do you mean by that?
Polynomial interpolation.
Oh, polynomial interpolation. Okay. So that brings back to the question of interpolation. So I don't know, like how many of you have experienced with interpolation, right? So I mean, the dumbest thing to do is piecewise constant interpolation, right? You look at the nearest point and just take the value, right? It's not the most accurate, but it's extremely stable. You can't go wrong with that. The most accurate, in some sense, is polynomial interpolation. You take everything into account, and you fit a polynomial across all the points. And if the function actually can be well approximated with the polynomial, you get a very high accuracy interpolation. But actually, it's extremely unstable unless the grid points you use are spaced in a particular way. So you can actually go back and try a polynomial interpolation over a uniform space, and you can easily observe something called the rank phenomenon, which is, let's say, you just fit this over a Gaussian function, and you get extremely large oscillations around the two ends. So for polynomial interpolation to work in a stable way, you have to choose a particular type of grid spacing that is finer over the two ends and coarser in the middle. Okay, usually you take the root of some orthogonal polynomial or something. But anyway, so basically there is a trade-off in interpolation. You can choose a very stable but not so accurate schemes that is works for almost arbitrary grid spacing, or you can choose very high order, very accurate interpolation schemes that is very unstable unless you have very particular grid spacing. Okay.